Hi to all the viewers of this presentation. This research project, Passive Office Design Post-COVID-19, is prepared by Hala, Issmail and supervised by Dr. Hanan Talib in fulfillment of the Master Degree Sustainable Design of Built Environment Module Passive Design at British University in Dubai. The content of this presentation will be divided into 5 sections: introduction, the location, concept and design, IES simulation data, and the conclusion. The introduction will have an overview of the COVID-19 virus and the impact of the virus on workplaces and economy, the aims and objective of the project, the methodology and sustainability assessment. We are facing a global health crisis unlike any in the 75-year history of the United Nations. The COVID-19 virus didn't only cause a health crisis but also caused a social crisis by attacking societies at their core. The virus also increased inequality and global unemployment in the medium and long term. For this reason, it's believed that the COVID-19 pandemic has triggered the most severe global economic recession in nearly a century, causing enormous damage to health, jobs, and well-being. Looking at the numbers of the major drops of the economic growth, it's essential to create a social protection system to revive the economy and workplace security. The aim of the project is to visualize a passive design office project prototype and upgrade the workplace post-COVID-19 for the future crisis adaptability, respecting all the impacts and safety procedures. The objectives of the project is to create a base model based on a set of post-COVID design guidelines, to develop a passive model based on a sustainable assessment standards, to test 3 passive strategies, solar slab, skylights, and Sunspaces, and finally to have final optimized model with all passive and strategies model integrated. Simulation tools is used to investigate the design and passive strategies of the project, and IES software is chosen for simulation analysis for its advanced energy and thermal simulations. And Breeam, as one of the leading sustainability assessments, will be used to assess and enhance the building envelope specifications. Moving to the next section of the presentation, the location will be showed, climate analysis of the location, and site analysis. The office design project is located in UK, London, Wandsworth, and the site is free of obstacles for the further flexibility in the design, while having nearby residential areas and educational areas for possible future jobs demands at the selected area. It's essential to study the climate of the countries where we build our projects. The weather in London is temperate with an annual minimum temperature of 5 Celsius. December has the lowest amount of sunshine and maximum precipitation. Snowfall is more experienced in recent years in London between February and March, while the wind is prominent from the southwest and west directions. In summer, the temperature can rise up to 21 Celsius with 200 hours of sunshine between May to August months. July is the driest month of the year, while May is the least humid month of the year. On the side, the sun path is placed with the direction of dominant wind, the main road, and the possible accesses. Moving to the third section of the presentation, design guidelines will be presented, the concept of the project, design development, and passive office design. After studying the impact of COVID-19 virus over the workplaces and human lives, 5 main design guidelines are developed to adapt to the changes by the virus. The workplace will have smaller working areas and circulation to reduce the interaction between people. It will have integration of virtual reality in the working areas and flexible spaces to utilize the maximum of the area. It will have constant natural ventilation for healthier airflow and the integration of outdoor accesses. The main concept of the project is to adapt to the design guideline caused by the virus, the site, and the weather, where the design process will first integrate landscape and have outdoor working areas. Second, break the typical office building into smaller offices and allow outdoor vertical circulation. Orient the masses towards the south and maximize the solar gain. Test the three passive strategies and achieve an optimized office design with high thermal efficiency. 4 models were tested to achieve the best design criteria and guidelines. Model 4 is the best, developed by breaking the typical office building with one axis and circulation into pieces with high compact masses, where the glazing is facing the sun path. The base model is now more realistic with smaller offices areas, blocks, less circulation areas with possibility to access each block from outside. Working areas will have flexible components while maintaining the safety distancing. The blocks will have natural ventilation and LED spaces. Moving to the fourth section of the presentation, IS simulations, the base model, passive base model, 3 strategies model, the data comparison, and final optimized model simulation data will be presented. The base model is built on IS software with HVAC profile of a typical working hours and days of the office for more realistic data. The envelope of the base model has typical and standard construction properties with external wall U value of 0.29, 0.22 for the floor, 0.18 for the roof, with single glazing external windows. And the base model is placed in a straight line on site facing the southeast. For the passive model, 4 main components are improved based on Breeam standards: the orientation of the building, external wall properties, the roof properties, and the glazing properties U value. First, the passive model is oriented towards the south. The external wall of passive model is improved to blockwork cavity wall construction details with improved U value of 0.15. And for the roof, the flat roof warm deck system is implemented with U value of 0.11. For the external glazing, double window is implemented with the addition of argon gas in the cavity. After simulating both base and passive models, data can be compared. The passive model has achieved 41% savings of the total energy loads. For the temperature simulations, as per the software data, the minimum temperature is on the 8th of March and the maximum temperature is on the 20th of August, and these days will be investigated for all the models. The passive model has achieved almost 3 degrees higher on the 8th March, while on the 20th of August, the passive model has higher temperature as well, due to the south orientation and high thermal walls. The first passive strategy that will be tested is solar slab with integrated shading to prevent overheating on summer season. 3 scenarios are tested on IS. The first, no shading. The second, inclined shading based on azimuth and altitude of the sun on 20th of August, and a straight shading based on an equation of having 1.3 projection at 3 meter height. Floor slab for all scenarios are adjusted to have a high thermal properties with improved U value of 0.0979. The data of 3 scenarios are tested where option 1 with no shading performed best on winter season with less heating load, while inclined shading had much higher heating load where the shading prevented both summer and winter sun. Also, the straight shading option prevented the winter sun entry, which caused higher heating load as well. For this reason, this passive strategy will have 2 modes with movable shadings of minimal adjustment. In winter, the building will have no shading, where in summer season, straight shading will be applied. The total energy of the 2 modes of strategy 1 has additional saving of energy compared to the passive model energy. Also, the temperature is improved where we have 1 degree higher in strategy 1 model winter mode. So, in summer mode, strategy 1 has achieved lower temperature and better thermal behavior on 20 August. Moving to the second passive strategy, Skylights will be tested with both openings on roofs only and projecting outlines with openable vents in summer for natural ventilation. 6 scenarios are tested with openings on the roof only, having projecting skylight with the glazing of the void walls, or having solid walls at the void having only internal voids, or having the projecting skylight with enhanced properties. The energy load of the 6 scenarios are compared for the best thermal energy consumption, where it's concluded to have the best thermal behavior for projecting skylights towards the south with 5 number of skylights. The final model of strategy 2 has improved properties of the internal slab U value to reduce the energy loss through the skylights. The best strategy 2 model has actually higher energy than the passive model, which can be explained by the additional area of the skylights and energy loss through the roof openings or glazings. Looking closely on the thermal behavior of strategy 2 model, it has actually improved with 1 degree higher temperature than the passive model on 8th of March. The model has significantly cooled the building on 20 August, moving from 32 to 20 degrees Celsius at 2:30 afternoon. Moving to the third passive strategy, Sunspaces, that will be tested with 2 forms, the inserted approach and the projecting approach. The Sunspace should have movable walls for summer season to prevent overheating. 4 scenarios are tested on IES. First, with glazed roof blocks and internal voids. Second, with solid roof and solid side walls. Third, solid roof with a glazed side walls. And the fourth scenario is with projecting 1 meter Sunspaces with enhanced properties. The energy load simulation of all the models have actually higher energy loads, where the worst model is with glazing roofs, assumed due to the energy loss associated with the roof openings. The best model was with the 4 projecting Sunspaces. The strategy 3 best model has inclined roof, high thermal roof and side walls where glazing is only towards the south. The properties of the internal glazing should be carefully enhanced and the small vents to be applied. The external glazing will be openable in summer season. The best model of strategy 3 has energy saving of the passive model, mainly in cooling load due to the shading provided when the external glazing is open. For the thermal behavior in winter, strategy 3 model has lower temperature on 8th of March than the passive model. Further simulation was performed to investigate the model. The air temperature simulation data of the whole March month shows clearly that the direct gain of passive model performed better than the Sunspaces. Also, the psychometric chart confirmed this conclusion. The final stage of the passive office design is developed based on the simulation data of passive model and strategy 1 and 2, ignoring strategy 3 that didn't enhance the thermal and energy behavior of the building. Final results comparing the base model, passive model, and the final optimized model with all the best strategies, passive strategies integrated. The final optimized model with winter and summer modes has achieved up to 52% saving of the total energy load. The temperature in winter of the final optimized model has 5 Celsius rise on the 8th of March. CFD simulations of the three models also shows the improvement of the thermal behavior of the building. MV internal CFD simulation have also conducted for the three models to investigate thermal comfort enhancement of the passive and final optimized model, moving from -1.8 to -0.7 at the big blocks. CFD external simulations has also performed for the three models to investigate the pressure impacts on the models. The passive model has lower improved wind pressure, while final optimized model has more distributed pressure due to the skylight additions. Summer season was also investigated, where the temperature dropped from 31 degrees to 20 degrees at the final optimized model at 2:30 afternoon. CFD internal temperature simulation also confirmed the finding with a much enhanced and lower temperature at summer of the big blocks. PMV simulation testing the occupants' thermal comfort has majorly dropped from 0.4 to -0.5 at the final optimized model due to the cooling effects of the model. This can be controlled and reduced by the percentage of the glazing openings. As a conclusion, a summary of findings is highlighted. The office building designed to adapt to site climate and, most important, to the design guidelines concerning COVID-19. The passive model was developed based on 4 enhanced properties following Breeam sustainability assessment. The passive model had 42 energy saving of the base model. The strategy 1 solar slab was tested with 3 scenarios and performed 17% extra energy saving of the passive model. Strategy 2 Skylights was tested with 6 scenarios. The final model consumed more energy than the passive model but enhanced temperature and comfort levels. Strategy 3 Sunspaces was tested with 4 scenarios. The best model of Sunspace didn't enhance the energy consumption or comfort level. The final optimized model of passive model properties, strategy 1 and 2, had total of 52% energy savings. The final optimized model has significantly improved the comfort levels as well. And finally, it is believed that the model has achieved the aim of the project and the passive office design post-COVID-19 is developed. Thank you for watching.